Hello, September 2nd. Alright, we didn't do it yesterday, so ideally I want to go back, investigate again. I kind of lost interest to figure out myself. Let's see what we have today, and we'll set the half an hour rule for sure. It just can't be more than that. We take a look. If it doesn't work, we'll just go ahead and then read the hints or whatnot. We just get it resolved. Find a number of ways to place people. I think this looks similar to what we have yesterday, so maybe we should read yesterday's solution first. Each pair, if they're not on the main diagonal, then check whether there are any other points inside the rectangle. That's exactly what we are trying to do. When there are only 2 points, the third loop is never entered, so we need to handle this case as a special case directly. Oh. Huh? Okay. Yeah, I know how this one's done, but I'm not gonna redo it. It's just brute force. Okay, now I'll go back here to the array points representing the integer coordinates of some points on a 2D plane where we have x and y. We define the right direction as positive x and the left direction as negative x, up and down. You have to place n people, including Alice and Bob, at these points such that there is exactly one person at every point. Alice wants to be alone with Bob, so Alice will build a rectangular fence with Alice's position as the upper left corner and Bob's position as the lower right corner. And the fence might not enclose any area. It can be a line. If any person other than Alice and Bob is either inside the fence or on the fence, Alice will be sad. Return the number of pairs of points where you can place Alice and Bob, such that Alice does not become sad on building the fence. Note that Alice can only build the fence with Alice's position as the upper left corner and Bob's position as the lower right corner. For example, Alice cannot build either of the fences in the picture below with 4 corners because Alice is at 3, 3, and Alice's position is not. Alice is 1, 3. Bob at 1, 1. Bob says is not the lower right corner. Hold a second. Bob's position is not the lower right corner. Huh? You said it can be a line. Why is this not right? I don't understand. 1, 3, and a 1, 1. I mean, I think what's trying to say is they cannot build a fence like this. Of course, because this is this, right? This is 0. So is this exactly the same as the previous one? We want to find the number of pairs such that within the pair, there's no other points. I think the only difference is now we have 1000, so this one will time out. I think that's the only difference between the two. Yesterday, we can do this. If you put in today, I think it'll work just as well. Yeah. The only difference is this one's gonna time out because it's 1000. Yeah, it's gonna time out. So exactly how we'd expect it to be. So essentially it's the same problem, but we need a smarter solution. O(n) squared. Maybe O(n) squared log n. I think we need to sort. I think we need to do exactly what we tried to do yesterday, but we failed. I think we need to sort on X. Now, sorting on X, the difficult part is, I mean, at each position, right, this, on each position, I can have multiple points with different Y's. Essentially, this is after sort what we're gonna have, right? This is what we're gonna have after sort. And we can control how we want these things to line up. So we basically say what Bob should be, right? And if we go from right to left, we say, okay, if Bob is on a 2, if we go lower, so we say Bob is this one, okay? If Bob is this one, then what we want to find is including this, right? Including this. Maybe we can use a map. Maybe map is easier. Like, seriously, map might be easier. We use order the map for X, and if it's the same Y, we push it in, and once it's done, we sort it. Like, seriously, we sort it. And after we sort, for each one, I can go with the smallest, and I always have this, right, for within this, and I go here. So for each one, okay, So as we go to the left, we want something that's bigger than that, yes. But at the same time, we need to make sure that when we draw this, there's nothing in between, which means when we have another y, we need to know if there is another value between these two y's. How do I make sure of that? Well, this has to be the smallest, right? This has to be the smallest. So what we need to know is between this and this. So what if I keep track of and I have a sorted list, right? Every time I push it in, we get a sorted list. So when we get this one, we have to guarantee we can binary search to see if there's anything in between. Nothing in between, that's a good one. And we try, and for each one we go from the small to large. The first one, right? If the first one works, good, and that's it, because the next one cannot work, right? Because I'll have the first one. So yeah, it'll be going like that. This might not be a bad idea. Okay, so we're gonna try this, and if it does not work, then we will check the solution. But here, first thing, sorted set, binary search. Can we do that? You can use lower bound and upper bound. Yeah, you can use a lower bound and upper bound. So, okay, another question. Sorted map from large to small. Oh, I can do greater. Oh, really? That's it? I thought you have to do a parentheses. No, parentheses is when you do the sort. This is different. Okay, so I think we have the tools. We just need to implement. This is exactly the same as problem, I don't remember, what's this one? 3025. Problem 3025. Except that the constraint is much harder. Constraint precludes the brute force solution. However, since n is no larger than 1000, we can afford a O(n) squared log n, right, solution. We will create a sorted map with x being the key and the list of y being the values. we then sort the y's as well, right? By we sort them directly, right? And then for each one, as we go through, we'll build this. Now for each, we go from large to small in x. For each x, it can always get, for each x, if there are multiple, for each x, so we go from the smallest, so we can use this, and then we go from here, right? For each x, we go from small to large in y. For each xy, we find the smallest, right? So we find the smallest is here, and then we move on to this. What's the smallest here? Smallest is larger than this, right? Smallest is larger than this, and smallest is larger than this. So each one we find the smallest is larger than it, and then if it doesn't exist, well, we find all the x's that are smaller. We go through all the x's. Okay, we go through that are smaller than x and find the smallest y that is larger than y. Right, smallest y that's larger than y. And then if this y can be, we also keep track of all such y's. If a new y can be added without having another y in between, right? Then we have a pair. So what we want is a map of int. I think I can just do a vector here because it's fine. So this is going to be axis map. Okay, and then we say for auto const auto p of points axis map p0. Oh, hold on, wait, I forgot one. std greater p0 dot pushback p1. Huh? I thought that was the definition. Too few template arguments for class. Or I actually don't know how this one is defined. I don't know. The map has int as key and vector as value. I don't know why it says it's wrong. I know why, because this one was not defined. There you go. Right, that's essentially what we do. And then for how do I iterate through map? Iterate maps values. Auto pair. Const auto pair of axis map. Sort. Second dot begin pair dot second dot end. Okay, so now read-only variable is not shoot. Okay, so now we sort them. Okay, we have to do a sorted set of int, but that should be wise. And that should happen at every single one. So here, so basically we get the first one, we pick it, and we sort it. Yeah, that's fine. I think we have to do it one more time. So for const auto pair of axis map. Alright. So now we go from the largest x to the smallest. And then for each, we need to go through every single y. Right, so we say x is equal to pair dot first. Okay. And then for into y of pair dot second. That's actually not the best way to do, so we should say I equal to 0, I smaller than pair dot second dot size I plus plus, and we say int y is equal to pair dot second I. Right, so we have x, we have y, and for each y we will create y's. Right, we have this y's, and then what we want to do is for each one we will go through that is actually not. Because for each one we have to go through everything. For this we have to go through everything. For each one we have to go through everything. Which made me realize that we should actually get vector axis So So now here is different. And I equal to access dot size minus 1, I larger equal to 0, I minus minus. So this is access I, the biggest, right? And then this is going to be j. Right, and then this is going to be access map j, no, ij. Oh shoot, this is I. No, not really, this should be x. Huh. Y along the way. Alright, so we got the x, we got a y is associated with the x. Actually, I don't really think it's necessary. I think we can just do here. So what we're trying to do? What we're trying to do is go through every single y for the current x. Right? Go through every single y for the current x. And then we'll go through every single x. And then we find the first one that's smaller. Right, so okay. So this is for the hx, this is for every single y. I do believe maybe I can just go map x. I don't have to do this. Alright, so now we have x and y. So for this x and y, what we're gonna do is go through every single possible, right? Now we go x over here, then we go da. So we get the first one that's smaller or equal, that's bigger than, yeah, okay. So we say for, so then go through all eligible points, right, to the left and up. Eligible points for, so let xy be Bob, right? Be Bob. We will go through all the eligible points for Alice and check how many will work. Okay, so we have int, we use ij, let's use pq. So p, this we do x should be the same as I, right? Same as I, it cannot be larger than I, right? And then p should be larger equal to 0, and then p minus minus, right? And int xx equal to access p. But honestly, I think access is required. And then for int q, for each one, yeah, let's just go from 0. And then q is smaller than access map xx size q plus plus. Okay. So if int yy shall equal to access map access q, right? Then we say if yy is smaller than y, smaller or equal to y, right? If it's smaller or equal to y, continue. because we don't consider that. Else, now we have a situation where x is smaller and y is the smallest, right? And then here is where we will do the set thing. Y along the way, right? So yy is a candidate. Now, xx yy is a candidate. Xx yy is a candidate. Alice. We need to make sure that there is no other y between yy and the y value between yy and the y. So here I should say I can actually do y. We'll put y in here for sure. Right? So we need to make sure. How do we make sure? We can use either upper bound or lower bound. Lower bound. The first element that is not less than key. The first element that is not less than key. It can be the same. It can be the same. Which means if it's equal to if it's equal to, if I have something there already, because x is smaller, but y is the same, then you can't. You can only do it once, you cannot do another time. So yeah, so you put this one in, right? And then you want to see, that should be upper bound, right? It should be the upper bound of this y. That's the first element that is greater than key, right? First element that is greater than this key. So there will be a value, and your value, like if I have something like really here, right? If I have something like here, then none of these will work, right? Because there will be nothing. We hit this, and we cannot hit like any of these. These will all be in it. So yeah, essentially the first. So essentially you go for this, you put it in, right? And then you go for the here, and you do the lower bound of the upper bound of this, and it gets some value. And you say, yeah, this is in between the two, so I can put it in. And then when you do upper bound again, you need to, so it only can be only one. Okay, so I don't think we should do this. This is not necessary. Right? And here we essentially say the first one, like if it's empty, right? If this one is empty, that's fine. We can always put it in. And then we will do upper bound. Okay. So if it's empty, I think upper bound will also return. What does it return? Iterator, right? So essentially the iterator, ooh, that is the issue. So this will tell me upper bound. Okay, this will tell me the upper bound. I don't need the upper bound. All I need is to keep track of the smallest y that's bigger than. That's all I need to keep track. I don't even need to use this. Just keep track of the smallest. If you're smaller, I'll keep track of you, right? If you are you get something bigger, then I say, yeah, it's not possible because something else is already there. Which means all we need to do is not a set, right? This shall be an integer, which is the smallest that's bigger than it. And when a new one comes, yeah, so we say min y, min larger than y, minimum. How do we do this? Well, I can just do it in the max, which is perfectly fine, right? So we are in this x, we go through all the y, so we find the first y as larger than, then basic we say if yy is smaller than mean large this, right? It cannot be equal, but it can be smaller than. So if it's smaller than that, then that counts as a result. So I'll do res equal to 0, right? So what I'll do here is I say res will be plus plus. That's a pair. And then mean larger than y will be yy, right? And if it's larger, then we just break. Which means regardless, we'll break here. Alright, so if it's smaller, then we'll record it, and then we'll break. Because there's no point keep doing. Because you get another one that's bigger, you cannot do it. But if it's bigger already, then we break. So we always break, which means I can simply do, say, yeah, because if it's smaller, I have to let it. So if it's bigger, right? If it's bigger, the first time we find it's bigger, then we need to, hold on. So what you're saying is if this is bigger than y, yeah, I'm gonna do some refactoring now. If it's bigger than y, right? If it's bigger than y, now we check if it's smaller than. If it's smaller than, I update this. If it's not smaller than, but we'll break. The first time we hit, we'll break. Okay, so this is we hit all the y's, right? We get all the y's. Now, after we get all the y's, now what do? We finish the current, now we move on to the left. So P, keep going, and then we'll do exactly the same thing. We'll find the first yy that is larger than y. That's larger than y. It cannot be y. Yeah, the first one that's larger than y, and then we'll check with the minimum larger than y, right? We'll check. If it's smaller, it cannot be equal, because if it's equal, we have something before already, so that's not gonna be right. But I just realized one thing. You said this has to be large. I think it should be larger or equal to. That's the trouble, right? That's the trouble. Because technically we can do one, right? Technically we can do one. Hold on, let me think. So okay, this y must be larger or equal to y, because it can be equal to y, right? It's larger or equal to y. Okay, so I say it has to be larger or equal to y. The first one that's larger or equal to y, and it cannot be the same. Okay, so large equal to y, and xx is not equal to x. That's not true. I think. All right, I think if y is equal to y and x is equal to x, this is the edge case. Will continue. All right, this is the edge case. Okay, so otherwise, if y is larger or equal to y, it's a candidate. Then we check if it's smaller than the minimal, right? If it's smaller, then we update this. If it's not, even if it's equal, that means we already had this before, right? We had this before, then we cannot handle it. Okay, so that looks good. All right, that looks good. And once this is done, we go back to the x, so x move on to the previous one, right? Move on to so we have a smaller x, and again we go from the lowest y, right? We go from the lowest y, and we'll get hold on. So we have, oh my goodness, we have x and y, right? We have x and y, and then we set this, and we go from this, we go through every single one, and we update the minimum larger than y. And once this whole thing is done, okay, once this whole thing is done, which means we go through everybody, right? We go through everybody, and and then I will update the y. Now y move one spot higher, right? And then we'll reset, and we again do the same thing. We'll do the same thing, and then we go, okay, so maybe. So after this, then we'll return res. I'm not sure, but I noticed that the time is already 43 minutes. So if things go well, maybe this one will work. If it does not work, then it does not work. Ugh. Lordy. It does not work. It worked for the third one. It doesn't work for the first two. Output 0. Output. That is very weird. What's the first case? Example 1, it should be 0, but I got 2. Alright. I don't understand why I got 2. So we'll have like 1. We'll get 1. Of course, it should be 3 get 3, 2 get 2, and then 1 get 1. Right, that's after this. And we have x, that should be 3, 2, 1. Huh. You're going x from right to left. Which means, I mean, for crying out loud, I think you can use unordered set for this one. Unordered map. Yeah, let's make some changes. I'll use unordered map. Because you have to take it out, and there's just no reason to do the other way. Yeah, we have unordered map, and we have to do this. We have axis. We'll sort this, push it back, and just sort one more time. Axis dot begin, axis dot end. Now I can go from right to left. Right now this one will be okay, hopefully. Try it again. All right, let's we have a test case. Let's see if it works. It will be amazing if we solve this difficult one while we did not solve yesterday's easier one. That would be very, very interesting. All right. It's done. It's done. It works. Oh, crying out loud! It works. A terrible runtime, but I don't care. It works. It freaking works. Yeah, it just I don't know. I mean, maybe yesterday my performance fluctuates a lot. Sometimes I got tired, I don't feel like doing it, and things can go really wrong. Of course, it's terrible runtime, and we can definitely make it better. I do think we can make it better. Honestly, I actually don't know. Maybe we can terminate this one earlier. Maybe. I mean, essentially, we have a y, right? We have the current y, and we draw a line. We have a current y, and then we want to draw a line. We want to get the ones, right? Get the smallest ones. So for each one of them, we could do a binary search. So instead of doing this, right? Instead of doing this, we have to go through all of them, which can be very time consuming if this y is big. I can do binary search to find the upper bound, right? The upper bound. That's actually an interesting idea. Let's try this. So instead of doing this, I will find the upper bound for it. So I get the xx, that's fine. And I'll say auto yy's shall equal to axis map xx, right? And then we say auto it is std upper bound. Okay, upper bound yy stop begin, yy stop end, and we put y in there. So this is finding the smallest value that's bigger, right? That's the upper bound is This is the first element that's greater than the key, right? First element that is greater than the key. Okay, so we find first element that's greater than the key. And it can also be equal to the key, right? That's the thing, it can also be equal to the key. So it's not just that. So if it is equal to yy star end, continue, this means there's no y that's bigger. Honestly, no, that's not true. That's not true. We shall always do -1 to check. Yeah, we should check, right? We should always check. So I need to do this. I think it's std distance. Yes. Okay, this is a wrong idea. Hold on. std distance. This and yy.end. So this is index. Okay, so we can say index is this. If so, there are two scenarios, right? There are two scenarios. So I need yy, right? I need yy. So I can say int yy. If y's index -1 is equal to y, right? That's the equal, right? It's equal to y. Then yy is equal to y. Else, so it's not y, it means it's smaller than y. Now we have to say else if index is equal to yy's dot size, right? And in this situation, we should just so for this x with binary search and didn't work, then we should continue, right? So this basically continue. This is no y is larger than y. Okay. Else, this is a situation we have something. So yy shall equal to yy's index. Okay. So that's how we get yy, and this will still work. Actually, hold on. Let me do this, the whole thing. And we can delete this one. Oh, oopsie doozy. Shoot. I think blah blah is 4 is needed. This is needed. This is needed. Maybe this one is not needed. There we go. What the hell? Hey, this one's not needed. Okay. All right. Yeah, we have the index, so we say if the one smaller is equal to y, then it has to be that one. Otherwise, if it's already there, then we just continue. We don't deal with this one at all. We move on to the next x. And otherwise, we say y is equal to the smallest one that's bigger, right? And then we say this is a candidate. And we need to check if this, right, and only this, and we don't need to break because this is done. Now we move on to the next one. All right, so let's see if this one is correct. So we say update, use binary search to find the minimum yy that is no smaller than y. Hopefully this one works. Let's go back here. I want to use this one still. Oh. Maybe it should be end as a first. Well, that's likely. Nope. Alright, how about we just do this? Not sure. Addition of unsigned offset. Undefined behavior. Oh, I think I called it wrong. God, Lord. I think, wait, hold a second. Really? How do we call upper bound and lower bound? I don't remember, man. I don't remember. I don't want, yeah, first, last. Oh, hold on. Upper bound, lower bound. Upper bound, vector. Yeah, begin and end. We're gonna it. Oh, begin to it. Ah, that's all right. So why stop begin? Yeah, I don't know. It's that was a pretty stupid mistake, honestly. Not sure how this even work. All right, now we get index is begin. Okay, let's try one more time. We're closing on 1 hour. Oh, what the hell? Index is 0. What does it mean index is 0? It's just the upper bound. So the smallest thing is this, right? That's I need to know why. So in this case is all right. So index has to be larger than 0 and this. Huh. That is bizarre. That is bizarre. That is very bizarre. I thought it was the same algorithm. Yeah, I was trying to find the upper bound based on the y, right? Trying to find upper bound. So we find the first one that's bigger than y. Yeah, first element that is strictly bigger. First element that's strictly bigger. And that's how you get the index. I think I know. I think I know. There is one thing I do here I didn't do in this one. This. Holy crap. So it's index would be this would be this, and xx is not equal to x. That's the only time we can set. Otherwise we cannot set. There we go. Let's see if this one is any faster. Nope. It's even slower. Okay, yeah, screw this. We will not even consider. We'll use this. Let me copy this. Yeah, we'll switch to this one. And we will do this. Okay. That will be it. I think I'll read this, but some other time. Yeah, again, it's strange. We didn't solve it yesterday, but we were able to solve it today. Which means that this one, if we copy and paste into yesterday's solution, it will work. Alright? It will work. Let's try it. If we do it, it shall work. So this is the same solution as problem this. We'll give it a little run. Yeah. There we go. It's faster than this. Yeah, understandable. Okay, that would be it.